Welcome everyone for the last session of the first dam safety conference. For the last session, I like to invite to the dais the chairman, Sri R. Subramanian. Mr. Subramanian is working is the chairman of the Kaveri Technical Cell Interstate Water Commission. He is looking after the Water Research Division of Tamil Nadu Interstate Water Dispute and Interstate Water Issues. He has experience in basin planning, hydraulics, structure design, and water resource management. He works as a faculty in Anna University and work in the government of Libya. He published more than 20 technical papers in national and international seminars. Then we have among us the co-chairman, Sri R. Jayasilan. Mr. Jayasilan did his BTech from University of Madras and subsequently MTech from IIT Madras. So he is our alumni. So after the MTech, he did PG diploma in Norwegian Technical Institute in hydropower, and he joined Central Water Commission in 1969 as assistant director. So he has 30 years of service in various water resource projects in CWC. He handled projects in Afghanistan, Oman, Laos, Myanmar, Indonesia, so all over the globe. And he worked in water and power consultancy services, India, for 7 years as a consultant. He has more than 13 technical papers in national and international conference. We also have rapporteur Sri Sibbal Ghosh, Director CWC. Mr. Ghosh did his BTech from Calcutta University in 1982. Subsequently, he did ME from University of Roorkee, now IIT Roorkee. He worked in EIL Engineers India Limited from 1982 to 89 in various projects of national importance. Later, he joined CWC through IES in 1989. He worked mainly associated with design wings and responsible for many water resource projects in the field of dam and barrages. So I like to handle the session to Mr. Chairman. And thank you.
After a good lunch, we are assembled here for the technical session 6. My colleague, Mr. Jayasilan, co-chairman for this session, and Mr. Ghosh will be the report here. And in the list given to us for this session, 9 papers have been listed. And apart from that, one more paper has been given to me. If time permits, I can allow that also. The papers are quite interesting papers. First paper is by Mr. Pillai, who is handling the dam safety project. I'm sorry, there are only 5 papers now. One more has been given now, one by Mr. Padmanabhan of Public Research Department on the topic hydrology review study of Vaigai Dam. And if time permits, we may allow that also. And I would only request the authors of the paper to be brief. The time available is limited. So we can at the most allocate about 10 minutes each paper. One moment. And I would like the co-chairman to say a few words, comments.
Good afternoon. I'm mainly happy to be here for 2 reasons. One, for the invitation extended to me to participate in this, and the other is, as already announced, I did my MTech from this institution. And also earlier in one of the seminars, I delivered the keynote address right in this place, coordinated by Professor Mohan. So it brings back to me all the old past memories, and it is getting renewed. Our chairman started with this statement: after a good lunch, just to deviate from our normal technical mind, I would like to say something. See, there was a preacher who used to be very long. So what happened one day, an old lady with a grandson came and sat in the front. As he continued, this old lady started No, sleeping. So the preacher was a little irritated. He indicated to the boy, wake her up. He just kept quiet. And he did it a second time. And third time he did this. He got up and he said, you put her to sleep, so you wake her up. So that's an indication for the presenters. You won't be doing that. Well, anyway, that's just by this incidental remark. And one thing that I would like to stress is, you see, the title is very right. It says compliance with the provisions of design standards. I would like to not only make it bold, but underline it also. Why I am saying this is, this compliance is lacking now. For various reasons, the design standards and design provisions are being sacrificed in many of the new upcoming projects. And also in some of the old ones, the maintenance standards are also not being followed. Though we speak up so much, in practical implementation, there is a lot more to be done. So I would like to stress this word, compliance with the provisions. Let us take it to our heart, every one of us, and do it religiously. Okay, the remaining remarks, I'll make it in the end. Thank you.
Now I would like to call the first presenter, a brief study of Orchdam's behavior by Mr. Smith Ubik.
Thank you, Mr. Chairman. Dear colleagues, dear Chairman Committee, I have been given credit and opportunity by the Conference Experts Board and the other two authors of that article to present that sensitive but attractive topic for arch dams. The paper deals with unusual behavior of arch dams, which are exhibited in the way on their long-term behavior, then slowly irreversible behavior unusual, meaning that the dam deflects counter to water pressure. And that, apart from that, the dams upheave the central part of the dams. I'm talking about central part of the dams. In a number of the case histories that were used as references for this paper, there were mentioned also that the continuous cracking in the upper galleries during the time of unusual behavior of dams appears. That study has two sub-subjects here. Then the one subject, we tried to collect the latest case studies of the dams behaving that way. And what is the substance of that paper? It is the authors tried to define mechanism why, to estimate, not to define, but to estimate mechanism why the dams behave that way. So that is substantial part of the article. I would start from the causes that we believe can cause such an behavior of arch dams. They were classified in general to be delayed deformation due to mechanical stresses, delayed dam deformation due to chemical process in the dam, and combination of these two causes. As for number one, we can emphasize creeping of the concrete as a reason of long-term, irreversible, and slow behavior of the dam. Then creeping of rock mass sometimes may be the reason. Then foundation movements can be the reason sometimes. As far as the chemical process is concerned, we are talking about swelling of alkali silica slow reaction, chemism, then delayed anhydrite formation chemistry, then open joint carbonation chemistry. All these can, under the certain conditions, drift the dam unusually, seasonally, and unusually. I will start first for alkali silica slow reaction. It is one of the most exploited topics nowadays in the current literature publications, etc. What is the model of that, chemical model of that? Alkali of cement reacts with reactive minerals of the aggregate of the concrete, causing alkali silica presence, which in the presence of the water swell. It is very important to note that that gel formed by alkali silica reaction is within the aggregate fragments of the concrete, not within cement paste. At the end of the day, in case of long-term performance of that chemical disease, I will call it, of the concrete, that may cause the swelling of the concrete itself. I also wish to emphasize that as a catalyst for this process, they are concrete temperature, which the available case studies emphasized as a benchmark 60 degrees, and also pore water in the concrete, moisture in the concrete. There were a whole variety of the rock mass that ranges from igneous one to sedimentary rock masses, which can be subjected to slow alkali silica reaction. Well, here you can notice an hypothetical arch dam, central cantilever of an hypothetical arch dam, and the time-delayed process of dam deformation taken from case studies. It is worth to emphasize that here you have the formation of the dam upstream. It is red line, the formation of the dam upstream under the presence of the water. Also, the expansive reaction might have his phases: initial one, development one, and slowdown one. Slowdown, a great number of the case studies indicated that alkali silica slow reaction process is long-term process and asymptotic process and leveled off process, meaning that the formation of the dam after certain time, which might be from 5 years up to 30 years, up to 40 years, the dam asymptotically finished his deflection. There are also the cases, apart from that, which, because of the impairing of the concrete strength and integrity, the arch dam, there was one case in Switzerland, had to be completely demolished and another dam constructed instead. It is a long-lasting, chemically irreversible process, meaning that the formation of the dam, the process impacted, produced, are also irreversible, are non-returnable. The main issue here is mechanism for such an unusual deflection of the dam. Why it is deflected that way? Well, it is our interpretation and assessment that is because of interaction of the swelling process and the stress fields imposed by service load conditions. Here, it is usually happened that during the low water levels, usually during summer periods of time, the dam and higher temperature of concrete due to environment temperature, the dam by itself deflects upstream. Is it finished? No, give me some more time, please. I will be fast as possible. The tensile stresses due to service loads develops up the upstream face of the dam, and they are complementary with swelling stresses, with swelling of the concrete. While the downstream zone of the dam, where we have compressive stresses, the swelling of the dam is slowed down because of counter effects of compressive stresses. I could recommend that if the service stresses are about 6 megapascals, then they can completely suppress the swelling of the concrete there. That is the mechanism why the dam seasonally deflects upstream. It deflects upstream, and it is captured because it is an irreversible process. It is captured, it is reversible, then waiting for another season, and for another season, and for another season, etc. The next topic, for which I also would like to request a certain time, it is delayed energized formation. What is the mechanism of that? Expansion of, there are the minerals of the aggregates, which are pyrrhotite and pyrite, which oxidize, resulting to sulfate ions. Sulfate ions, they expand, making since they expand, and the aggregate is not an expanding member of the concrete, they made a gap between the aggregate and the cement paste, in which the heterogized crystals can develop. The heterogized crystals are particularly developing under the following mechanism here, which is concrete supersaturation is becoming lower, and the service stresses are also becoming lower. It is unlike the alkali-silica reaction, it affects cement paste, not aggregate. That is the main difference between the delayed heterogized formation and the slow alkali-silica reaction. The mechanism, may I continue, please? The mechanism of the formation of the dam due to delayed atternage formation is very similar to that of alkali silica slow reaction. It became pronounced in the zones of tensile stresses of the dam. Again, we are witnessing the case of the interaction between the swelling process by atterngites and the current service stresses of the dam in the dam body due to service loads. That is the case with the lower water level and higher temperature of the concrete. There is another issue which I wish to bring to your kind attention. Why is cracking within the upper stretches of the dam, within the galleries? Why it is happening that? Again, because of interaction between the swelling process and the current stresses there. Due to lower water level, but minimum concrete temperature, there might be tensile stresses developing around the galleries. Those tensile stress field, in conjunction with the swelling process, can cause cracking of the galleries. Creeping of the concrete is another phenomenon which deserves our attention. It was creeping in the article, in the paper, it was emphasized specifically creeping of the concrete due to compressive stresses. We don't have enough material to analyze, we didn't have enough material to analyze creeping due to tensile stresses. Where we can suffer creeping of the dam, of an arch dam, it is that area that area here, which while maximum water level can be overstressed and then could creep under certain conditions if the original design was not absolutely properly made, say. A creeping of the arch dam, of the concrete in the arch dams, it is a complex process, please, and there is no much information about that. There is some empirical approaches which we are taken by the Ross Dam, United States. There is an empirical formula, and you can see here that the total stress per unit total strain per unit stress is reducing during the time. There is another dam, which is Zevreila Dam, which was combination of monitoring and computation of the dam, and you can notice leveling of process of the strains during the years within the dam. That indicated that creeping of the dam again could be under certain conditions leveling of an asymptotic process. There is another issue, which are the joints of the arch dams. Every arch dam could have joints. It is due to technology of construction of that kind of the dams, in which the mechanism of calcium hydroxide within the concrete paste could react with water, which can capture carbon dioxide and produce calcium carbonate and water. Why? When it happened while. Okay. Another few seconds, please. And It happened during the time of the high water, high environmental temperature, and high concrete temperature where the block joints open. Conclusions are already emphasized here and there. I wish to thank you for your attention, and I'm really sorry why I didn't have more time to explain in more details the other issues of that very important topic. Very important topic nowadays for all dams, including the arch dams. Thank you for your attention, and merci de votre attention, mesdames and messieurs. I am afraid that as far as that dam is concerned, I would not be able to.
Okay, thank you.
Pleasure.
The next paper is on basic design provision for existing dams. I think Mr. Mathur is going to present that.
Good afternoon, respected members on the dais and friends. Our paper is on basic design provisions for existing dams, not new dams. So, the various aspects which are required to be looked into while reviewing safety of an existing dam are the first thing is design flood study review. That is the first thing to be done. Next is to carry out a flood routing study and to work out the new MWL. Then to check the adequacy of freeboard for that revised MWL. Then look into whether there is a need or otherwise of providing an additional spillway, or if a parapet wall is not there, then probably a parapet wall, whether it would work or not. Those aspects. Then we are also required to look into the examination of various causes of distress in the dam. There could be excessive seepage through the dam, could be some wet spots, lot of water in the galleries, leaching, cracking in the dam due to various causes, damages to concrete in the spillway, mainly abrasion damages, energy dissipation. Slotted roller buckets have a lot of problems. So do have many stilling basins. Indications of any piping, boiling, things like that on the downstream of the earth dam. Then we may have to check the stability of the dam and spillway due to the revised MWL on account of revision in design flood. Then on account of changes in seismic parameters or change in seismic zone. Then there are issues related to hydromechanical equipments, outlet works, and things like that. There are a lot of other aspects as well. In general, our BIS codes and standards, they provide us guidelines for designing new dams. The same standards we have been using for the existing dams also. However, it is felt that while applying our standards for safety evaluation of existing dams, some changes perhaps could be considered or may be necessary. In this paper, I tend to dwell on those aspects in respect of a few subjects. The first aspect is the freeboard aspects. So the relevant BIS codes I have listed there. IS 10635 is on embankment dams, and 6512 is for the gravity dams. So what these codes provide is that, the 1 meter solid parapet wall on top of the dam is not to be considered as part of the freeboard. We don't consider it as part of the freeboard while designing new dams, whether it's an embankment dam or it's a gravity dam. However, for existing dams, because the flood many times goes up two times, 3 times, and like that, there may be a need to make some deviations in this. So what I propose is, and it's for the August gathering to consider, for an existing embankment dam, the solid parapet wall could be taken as part of the freeboard, in case the parapet wall is otherwise structurally safe. The second thing is, the maximum water level for the revised flood should be lower than the top of the impervious core. So this we need to ensure for an earthen dam. And for existing gravity dams, maybe the revised MWL could be allowed to reach up to the dam top, where a 1 meter solid parapet wall is there. So these are not just my ideas, these are also, some of them are also given in the USBR and various other literature. Then there is the issue of consideration of 10% gates as inoperative. IS 11223 guidelines for fixation of spillway capacity says that this condition is to be checked, and it is to be considered as some sort of an emergency condition, and a reduced freeboard could be acceptable. So we have been following this condition for the design of all new dams. However, for existing dams, probably we could make some deviation here. As I said, the flood after revision goes up 2 times, 3 times, and maybe more, 4 times, 5 times. So in general, probably I feel it's probably not, there may not be any need to check an existing dam for this 10% inoperative inoperative gates condition. However, we have to make sure that all the gates are in working condition, and all the O&M guidelines and all those things are being followed. Then coming to the third point is the stability analysis of an existing stability dam, earth dam. So this is basically with respect to the method to be used for analysis. Supposing we are required to check the stability of an existing earth dam, then method to be used for analysis. So IS 7894, this is the code of practice for stability analysis for earth dams. And the methods discussed in this code are the Swedish slip circle or the Fellenius method, and sliding wedge method for rock fill dams. The Fellenius method, it considers only the moment equilibrium and not the force equilibrium of slices. It provides a factor of safety generally on lower side, and results in a conservative design, which is fine for a new dam. But then there are other methods of stability analysis also, and I have listed a few of them here. There are others also: Bishop's method, Janbu's method, Spencer's method, Morgenstern Price method, and etc. So probably it may be preferable to adopt a method which satisfies both the moment equilibrium as well as the force equilibrium, and which takes into account the interslice forces and results in a closed polygon. The methods recommended, which could be considered for carrying out stability analysis of an existing earth dam, are Morgenstern Price method and Spencer's method. And we could make use of softwares like Slope W of GeoSlope. What happens is that Fellenius method gives a low factor of safety, and if it's an earth dam, making any changes in an existing dam is difficult. So if we are checking the stability of an existing earth dam, and if we use these methods, probably we may get a safe factor of safety, a factor of safety which is adequate, and we may not have to do anything on them. Then the next point is stability analysis for an existing concrete or a masonry gravity dam. This is with reference to permitting cracking in the dam. So as per IS 6512, which is the code of practice for design of concrete masonry solid gravity dams, we do not permit cracking in dams. Cracking is not permitted for any new dam. No tensile stress is permitted in normal loading condition, which is our general condition B, reservoir at FRL with drains operative. However, some tensile stresses are permitted in other conditions, like condition C, reservoir at MWL with drains operative, load combination E, reservoir at FRL with drains operative and earthquake, reservoir MWL with drains inoperative, and then reservoir at FRL, drains inoperative and earthquake. So these are some nominal tensile stresses which we permit. So what I am suggesting in this paper is to allow for cracking in conditions if the tensile stresses exceed these permissible values in case of conditions F and G, which is reservoir at MWL with drains inoperative condition, and then reservoir at FRL with drains inoperative and earthquake condition. For these two conditions, if the tensile stresses are coming to more than the permissible ones, probably we could allow for cracking. And we could follow the approach of USBR, which is given in the publication Design of Small Dams. The methods are fully described in Design of Small Dams. I am not getting into that. Only I am listing out the assumptions which are involved. For static conditions, when I say static condition, I am meaning the MWL conditions with drains inoperative. So here the vertical stress distribution along a horizontal plane without uplift is assumed to be linear between the upstream and downstream phases of the dam. So this is the first assumption. The second assumption is the uplift pressure in the entire cracked width portion is equal to the reservoir pressure corresponding to the reservoir level, which will be the MWL in this case. Thereafter, the uplift varies linearly from that point to the tailwater pressure on the downstream phase. The crack extends up to the point of no stress. The uncracked length is entirely in compression. So these are the three assumptions. And the stability criteria which is followed when cracking is allowed is that we check for compression and we check for sliding stability using the uncracked base width of the dam. For condition G, which is the earthquake conditions and drains inoperative, there is an additional condition which the Bureau of Reclamations gives. So it says that in the crack length, the uplift pressures are assumed to be 0. So there is a crack length and there is an uncracked length. So in the crack length part, the uplift pressures are taken as 0 because they say that during an earthquake event, the opening and closing of the crack is so rapid that it does not allow the reservoir water and associated pressure to penetrate. So this is one assumption. This is an additional assumption. So if the sliding and stress levels are satisfactory, are found to be okay for the cracked section during an earthquake event, then there is a need to also check the post-earthquake static condition. And while checking for the post-earthquake condition, we should include the full uplift pressure in the cracked part also. And that's it. Thank you.
This long experience in dam design has brought out clearly what the criteria to be adopted. Hello? Switch off. Do you hear now? This long experience in dam design Mr. Mathur, with his long experience on dam design, has clearly brought out the distinction between what are the standard practices to be adopted and how the design criteria can be distinguished between an existing dam and a new dam. Say, especially in this seminar, the engineers who have come from different states who are involved in checking the stability of the various structures under the DRIP project. I hope this his talk could be very useful. Thank you. Now I would like to invite Mr. Raghunath. His presentation is on seismic response of every dam for a hypothetical great earthquake in Himalayas.
Okay, good afternoon to all of you, you see. So now anyway, my topic is on Tehri Dam actually. So generally when you Google, this Tehri Dam, you will see so many reports, so many articles, many experts have worked, so many things are there actually. So now you may be wondering, you see, whether, why do you require once again, you see, this type of a study or not actually, okay. So now there are basically two reasons, which forced us to look into these aspects, once again. The first one is, there was an article last year by Professor K.S. Waldia actually. Okay, he's a very eminent geologist and authority on Himalayas. So he published not on Tehri Dam, he just made an something like damming rivers in this Uttarakhand Himalaya. So here he has pointed out once again, the most of the sites is the seismicity and other things were not taken into consideration or something like this. And in this article he has even told that there will be something like fault movements, something like overtopping of dam, landslides and other things he has just mentioned as a geologist actually. So when I read this paper with interest, as a structural engineer we are more interested in numbers actually, because that is what is required to check this dam safety. So that is why we just we wanted to quantify whatever statements he has made actually. So this was our first this reason. Now other thing is after this 2001 Gujarat earthquake actually, government has pumped a lot of money in this earthquake engineering, and this has given rise to a lot of wealth of information actually. Like nowadays we have information on faults, recurrence rates, maximum magnitudes, digital strong motion data is available, then broadband data, metal properties, so many things are available nowadays actually. So now and of course this subject of engineering seismology is also nowadays it is highly advanced. So now we are in a position actually to simulate this ground motion, may not be so precise but in reliable fashion actually. So now recently in 2011 we have even brought out this report, we have consolidated all the information. We have brought out this report on the PSHA map of India, supported by this National Disaster Management Authority. So all this information we have compiled and developed this hazard map actually. Now all this information, even it is available at your fingertips, So we have even developed this whole report in terms of apps actually, and Google Apps, you can download on your Android mobile. So like the seismic hazard of India, you will get this type of an app. So all the informations are available actually. So like this is the one, the list of faults and other things which you can get from this app also. So like now if you zoom it in this Uttarakhand region, say, so the fault maps looks like this actual. So now this blue color, these squares are nothing but the location of this new dams are, this one. Tehri Dam is here. Now this is the state of Uttarakhand. You can see that most of these dams are located very close to faults, or they may be lying on the top of the faults itself actual, which makes a little bit scary when you look at this the figure actual. So now anyway, now what we have done in this aspect is, this regarding this Tehri Dam, the structural models, a lot of studies have been done, 1D, 2D, finite elements, so much information is available actual. But what is missing is a reliable seismic input which can be used to check the safety of this dam actual. So now in this we have concentrated more on generating a reliable seismic input, and so structural aspect we have not touched much actually right at this point of time. So now these are some details about this Tehri Dam. I hope this information is available net, and most of you may be knowing also, like the height is 260, and these are the natural time periods given in this THDC report also. So now what we have done is, so as already I told you, our interest is in generating reliable seismic input. Like if you see the past data and others say, the maximum magnitude which can be observed in this region is, 8.5 actually, based on some past seismicity and almost all the data, so GPS measurement, it shows that the maximum magnitude this region can feel is something around this 8.5. So what we have done is, we try to generate ground motion for this 8.5 as much accurately as possible actually. So now here, as already I told you, lots of informations are available. So we have done this, the finite element model actual. So like you can see, we have done the finite element model of the whole, this Indian itself, including the topography, bathymetry, everything is there. Now the metal properties, most of the thing we have taken from worldwide database, but since some metal properties are available in Indo-Gangetic Basin, then Tehri, this Himalayan regions, we have incorporated all the information provided by this NGRI and some other, journal articles. So now these are some of the our mesh size and other size. So the number of degree of freedom is something around 12.7 billion, and of course average distance, our element size is something around is 2 kilometers actual. So now this finite element mesh we have developed, and of course you cannot run it on one computer. You require a super computer which is available at our IIT. So this is our Virgo cluster we say actually. So now we have run this one. These are the basic equations of motion for our Earth. If you open any geophysics textbook, you will get all these equations for a spherically symmetric Earth itself, including gravitation as well as hydrostatic equilibrium. So now these are some of the basic equations which we solve using our finite element mesh. And finally, so now regarding the seismic force actually, which we should use to simulate ground motion, here also lots of data sets are available actually. So we ourselves are having one project from Ministry of Earth Science to quantify these seismic forces. So we have developed something like these stochastic models actually based on some past earthquakes. So we used this type of stochastic slip models to generate the slip distributions for 8.5. So like this is one hypothetical slip model for this 8.5 event. You can see the maximum slip is something around 10 meters actual if there is 8.5 earthquake. Like you can see Tehri and Roorkee, they are very, very close to this fault plane, and the depth to the top of the fault is something around 10 kilometers actual. So now when we simulate from our finite elements, you will get this type of displacements actual. You can see at Rishikesh, you see the displacement is something like this, and it is not coming back to zero, it is going like this actually, which indicates that after the end of earthquakes, you will see something like residual displacements actual. Now this is at Tehri, you can see the PGD is 75.19 centimeters, and after the end, it is showing some small residual displacements or something after the end of the earthquake actual. Now these are similarly displacements at several places like Dehradun, Roorkee and other places. So now once again, so these are displacements once again at Tehri for variety of slip models actually. If I change slip, what happens and other things. I'm just showing some two samples actual. So now you can see all the displacements are oscillating. They are not coming back to zero, which indicate some residual displacement is after the end of this earthquake actual. So now this is a PGD contour map for this Uttarakhand for this 8.5, and these are the dams and hydropower plants. You can see the PGD is as high as 3 meters actual in horizontal direction. Now this is similarly in vertical direction. The PGD is as high as 2.5 meters actual. Now these are the ground residual displacements, that is after the end of earthquakes, which you will see as some cracks or openings or something like this. You can see this in east-west and then north-south direction, but this is a vertical displacement actually. You can see the uplift is something about 2.5 meters actual, which means after the end of earthquakes, you will see the whole land will rise by something around 2.5 meters. Now physically, what does it tells us actual? So like this is one spectacular dam failure in the Shikang Dam in Chichi earthquake actual. This dam was built on the top of the fault itself actually. So when the dam is built on the top of the fault itself, you can see during this earthquake, this portion has raised by 7 meters actually. So now you can see there are no cracks, nothing, but this dam failed due to this, this peak ground, this residual displacement actually. The same figure, if you see from other side, you can see this whole portion has raised by something about 7 meters actually. So now, so this type of things becomes very important in design, but when the structures are very nearer to this fault site, it is not just only the PGA, but peak ground residual displacement also is a very important parameter when you are designing dams very close to this faults actually. So like, of course, for this in our Uttarakhand regions, our peak ground vertical displacements are not as high as 8 meters. We got some 2.5, but when we simulated for some events in the northeastern region, especially in this, this 1950 Assam, the residual displacements are also as high as 8 meters we get actual. So now, of course, that is about peak ground residual displacements actually, which becomes very important when you are close to these faults. But when you do traditional vibration analysis, we require acceleration time histories actually. Now, whatever finite element mesh and other things I have shown, that is more reliable in simulating low frequencies such as displacements. But when it comes to accelerations, it becomes a little bit complex. So we have used some empirical Green's function techniques and others to simulate ground motion. And here also is in from in the last 5 years, IIT Roorkee has put up a nice network. We have a very reliable and very good quality strong motion data. So we used these things to simulate accelerations also. Like this is the fault plane, and these are the earthquakes for which you see we have the data at Tehri station actually. So now this is some Emperor EGF technique. Which one? No, that we have simulated from the finite element model actually, not from GIS. Yes. Yes. For Chichi earthquake, we have done that. No. Yes, we have done this one, Yes. Yes. No. Yes, sir. I understood your thing. See, like for 1950 earthquake in Arunachal Pradesh, there is one lake named Madhuri Lake actually. There you can see the fault upliftment of something around 6 meters. There was an artificial lake which was formed after the earthquake. No. This was the fault scarp itself actually. No, the lake was from the fault scarp we can see actually. Sir, yes. No. That is no. What I have done is this: we have these things are valid at rock level actual. As you rightly pointed out, if I include the geotechnical information, no. Yes. I told the 10 kilometer deep actual. No. What? See, no. As I already told you, this is not, we have done at rock level. Of course, we have to add one more geotechnical layer, and this may, it may not be like a rigid body. Some translations will be there. Yes. No. We are not claiming on anything on the dam design is safe. Nothing like that actually. No. No. I
You
just
should
showed.
not title it with Tehri Dam.
No,
That is
sir, I
very
will come.
unfortunate. If the region itself is moving, Tehri Dam as a part of it, if the whole hall moves,
Yes.
how do you segregate me and you say I am moving 8 meters? You have moved 8 meters. So the relativity question comes in.
No. Yes,
There are
sir.
many other.
No. I understand, sir. No. Let me.
No, my simple submission is that by virtue of this kind of statements, the whole dialogue of the development gets vitiated. And when you do not have a sound foundation in a particular kind of discipline, you should not try to extrapolate your conclusions to those kind of disciplines.
No.
This is a simple thing about that.
No. We are looking at as a scientist actually. We are not going doing this one.
But
See,
don't mix it up with Tehri Dam.
No, sir.
Kindly.
No.
You do your science, but you
But
have
this-
not come to Tehri. What is the period of Tehri Dam?
no, I just
And
showed
what
right 2
period
points.
you are dealing with it?
No,
you
no,
are
sir.
talking before, you are a scientist. I am asking you these questions. We have gone deeply. So
Yes.
unfortunately, these things are now trying to impede the very possible developmental areas which
Okay.
you yourself sized, and that map itself is questionable. You
Okay.
are putting a fault of about 300 kilometer length by
Yes.
15 kilometer width. There is no valid proof of that active fault. The nearest fault to Tehri is about 8.8 kilometer.
No, that is
And
a
you would use
no.
seismic gap theory. There is other philosophy which is, so this is all highly
Yes, yes, yes.
questionable. We have been debating it for over 10 to 15 years. To bring it, I think such things really confuses the mind, and unfortunately this was dragging back all of us. And how do you correlate with that type of other pictures? Do not mix up a picture of another dam which has moved 8 meters to compare with the, this is just.
No, there may be. No, sir. No, sir. No. No. No, sir. Please let me, see, there are two aspects are there. See, now that was for the displacements which I showed actually, PGRD, What I am trying to show is that is also an important, I am not saying that, this may have some other things also, but it's important thing. I'll just 1 minute, sir. So now we have even simulated this ground motions, also like acceleration time histories. So now one can see that actually. See our results, you see something like for this earthquake, we get something around 0.5 G actual, plus or minus some uncertainty of this one. These are some sample time histories and you see the response spectra. So now we have just done some preliminary work actually on this like 1-dimensional and 2-dimensional. We have not come to any like nonlinear things. We have not yet done this one, which may even reduce the final results also. So like these are some of the the responses of this theory dam. This is 1-dimensional model, 2-dimensional, what happens and other things. So some toy models we are just exploring actually what happens this one. Like these are some shear strains and other things.
Will you please come to the conclusion?
Yes, sir. So this is the final this one. So what I would like to say is anyway we have done only linear analysis. So when we do this acceleration this one, so we get something shear strains and then we get some 1 to 1.60. But of course this is ours is a linear model. So if you include non-linearity, so maybe these numbers will come down actually. And I just wanted to say I'm not making any generalized comment, but this also may have some importance or something in selecting these sites for this dams actually. Thank you.
Mr. Raghunath, this is a topic, it's a controversial topic, and as Chairman Central Water Commission has interacted, this has to be thought, rather much deep analysis has to be done on this. And as Mr. Gopalakrishnan has pointed out, the former Director General ICID was actually involved in this problem, knows more on this. So we can better interact with them. Thank you. Now I would like to call the other presenter, Mr. Srinivas, who will be presenting a paper on failure of spillway radial gate of Narayanapuram. Please try to complete.
Yeah. Good afternoon, dignitaries on the dais and off the dais. At the outset, I would like to thank all the organizers, the technical committee, for giving me an opportunity to present this paper. So I will be talking about the failure of the spillway gate of Narayanpur Dam, how a construction error as well as an improper maintenance schedule or inspections can lead to a failure. So the presentation is structured with some salient features of the Narayanpur Dam, followed by the genesis of the gate failure and the event itself, and the implementation with a conclusion. So the Narayanpur Dam has been provided with 30 numbers of radial spillway gates, out of which 25 numbers are in the main spillway and the 5 numbers are in the auxiliary spillway. It's of the size of 15 meter by 12 meter with a discharge capacity of 45,000 cusecs per gate, and it's operated with an electrical rope hoist mechanism, and it has been commissioned during the period 1982 to 84, and it has been fabricated and designed by TSP and Sika. The spillway capacity has been designed for about 13,40,000 cusecs with a frequency of 1 in 10,000 years, with 10% of the gates in non-operation condition as per the norms. This dam has manifested its distress signals even earlier to the event which I am now presenting. During 1990-91, there were some failure in the weld joints in some gates like 316 and 15, which was rectified by the fabricator himself. And in November 1992, the auxiliary spillway gate number 5 got damaged. And when the government constituted a committee to know its cause, we found out that the cause was the failure of the bulkhead gate. All these 5 auxiliary spillway vents, before the erection of the radial gates, were fitted with, 3 vents were fitted with the stop log elements and the 2 vents were fitted with bulkhead gates. But even after the commissioning of the spillway gates, the bulkhead gates were not removed from its position. So the bulkhead gate has failed during 1992, and the conclusion was that the cracks in the defective weld structures had propagated over a period of time, which has led to the failure of the bulkhead gate. So it also had some inherent shortfalls during the construction or the fabrication and erection time, wherein the skin plate and the wall plate was not matching in some gates. There were some improper fixing of wall plate to the designed vent width, and also the loss of curvature of the skin plate during the erection. So the gates committee made some recommendations which were attended, and ultimately that radial gate, auxiliary radial gate was replaced. So this is the main event which I was referring to. This is in 6th October 2005. The dam was at its FRL at 492.25 meters, and the central gates were in open position and surplusing. At around 11 a.m., the main gate number 5 from one end, it got dislodged from its position and was pushed into the river bed downstream to about 100 feet downstream. And the government of Karnataka constituted a team, and the experts made the inspection and recommended the depletion of reservoir to about 486.5 meters, about 6 meter depletion, which resulted in about 20 TMC of water being let out during that period. And for the next 2 days, the stop log elements were put into its place and the vent was pegged. So this was the view of the dam during that flood regulation, and this is a vent which has been pegged using the stop log elements. You can see that the trunnion and the yoke girder, everything has gone along with the gate assembly. Those are the stop log elements which are in place. So the committee also assessed and has come up with the sequence of the failure as to how this gate would have failed. So the sequence is, there was a failure of the joint between the yoke girder and the trunnion, which resulted in the disturbance of the trunnion and leading a huge strain at the junction of the arms and trunnion. So this led to the entire load of the gate coming on the left arm assembly, resulting in the bolts connecting the trunnion to the truss beam snapped. So in the absence of support on the downstream side, the skin plate assembly, which was held by the ropes, wire ropes on the upstream side, couldn't hold the gate in position and eventually snapped its connection with the skin plate. So the entire skin plate assembly with horizontal girders, left side arm assembly with trunnion slided along the spillway profile and was pushed out of the spillway bucket also and moved nearly 100 feet into the river. Similarly, the right arm assembly also was transported to the river bed. So this is the gate number 5, which was found in the river bed at about 100 feet from the spillway. And we can find the chairman of the committee, Mr. Dayan Desai, inspecting the gate at the river bed. So these are some photographs about a typical tie beam joined before the failure and the spillway gate tie beam left side, where we could find that the weld joint are not to the designed penetration thickness. So these are the photographs of the tie beam right side weld joint. What was found is that the weld was not properly penetrated to the trunnion proper, and there were some rods and plates were found to be placed in the weld gaps. So this was a finding of the committee, and after the inspection of the failure. So the causes of the failure was concluded by the committee as the failure of the fillet welded joints at the junction of the tie beam between the trunnions and the trunnion proper itself. And also the weld failure was due to a progressive rusting due to ingress of moisture and water over a period of time, and inadequate inspection and maintenance, which was limited to lubrication, replacement of wire ropes and seals, and periodic maintaining the successive years without actually going into the crux of the problem and attending to the inherent weld defects and other problems, because of lack of capacity of our engineers as well as due to frequent changing of our engineers in our bureaucratic setup. So the recommendations made were that all the weld joints be redone to the design thickness, the scale formation of the skin plates to be removed and painted, and the stiffeners which have lost thickness by more than 2 mm needs to be replaced, and also they strengthen the joints of the trunnion tie and the joint between the tie beam and the trunnion proper themselves. So these were implemented. The damaged gate number 5 was replaced in 2007, and the other recommendations of the committee regarding the strengthening and other aspects was covered in 2 phases from 2007 to 2011. And the way forward is that Narayanpur Dam has been included in the DRIP project. We are taking up a comprehensive intervention both for civil and hydromechanical components. We are trying to provide a zinc metallizing for the skin plates so as to arrest the further corrosion of the skin plates. And also to augment the emergency preparedness, we are making a provision for a gantry cane along with one set of stop lock gates as an estimate called of 5.36 crores. So in conclusion, I would like to tell that the hydromechanical components of a dam are as important as the main structure and needs utmost attention towards their upkeep and maintenance with systemic regular inspections. They are the lifelines of storage and safe discharge of floods and for preventing the loss of invaluable human life. The impetus should be towards the modern techniques of crack detection such as thermal imaging or ultrasound. I think the industry would need to help us in this regard. And we also need to have some emergency preparedness actions like stocking of welding equipments and all other allied equipments for tide over in the case of any failures. And also on the institutional part, what is required is that all the officers up to the level of the chief engineers are to be made responsible for pre-monsoon and post-monsoon inspection of dams. And in our state, we are having a DSRP panel along with DSRT teams, which are looking into the safety aspects of all our dams. And it is the strict compliance of these committee recommendations would go a long way in maintaining our safety of dams. Thank you, gentlemen.
Thank you, Mr. Srinivas. Your paper is very interesting. Many times when a failure occurs in a dam, engineers fail to report it, or rather publish it as a paper. So failure only makes us to learn and to improve our system. So that way your paper is good, and it is apt also for the DRIP project. Now I would like to call Mr. Handa. He will be presenting a paper, Failure of Angal Minor Irrigation Dam Investigation.
Thank you, sir. Good afternoon, everybody. Actually, this is a case of a Ankamal Dam in Bellary district of Karnataka. It's not a minor, but as per the height, it's a medium project. And the most peculiar thing about this is that this dam has failed the second time. Earlier this dam was built long back and no records were available for this project. And the dam was again constructed in 1988, and in 2010 it failed. And when we investigated the project, then it was found that probably the reason for the second failure and first failure could have been the same. And the dam failed on the night of 20th and 21st August 2010, and nobody saw it, and there were no records of earlier discharges and all those things. The height of the dam was 17 meter, the length 278, there is a spillway of 53.25, and the design discharge was 102 with a crest 5.9 meter above the crest level. Now the dam breached from the middle of the deepest section for a 71 meter length from 199 to 270 meter, and there was a rainfall of 102 mm for 9 hours. That was the only record which was helped us to find the cause of the failure. And the field observation, we generated all the data on the basis of the field observation and other things. The dam was inspected by Dr. Y.K. Murthy, who was chairman of DSRP, in December 2009, and about 7-8 months after that, the dam failed. And his recommendation was that the spillway should be designed for SPF. Actually, he suggested that spillway should be designed for 1 in 100 year and checked for SPF. But being a medium dam, I discussed with him that it should be SPF only, not 100 years. Then extensive damage to the bed pitching slab provided for 4 drop walls. That was before the failure. These were the things were reported. Then the freeboard was not as per the codal provisions. Stability was not done because rather there were no properties of the material by which the dam was constructed, and they were not checked anything for that. Then he said that few piezometers should be installed so that we can have the phoretic line and all these details. Then after the dam failure, one member of the DSRP was deputed by Dr. Murthy because he was not able to go to the site because of the health conditions. Then he submitted a report, and as per his report, about 1.5 meter depth of water over spillway from flood mark. He noticed a flood mark on the side of the spillway, which was showing a 1.5 meter. And with the rainfall data, they calculated made the hydrograph and calculated the discharge that it was 219 cubic maximum. And his findings were that the flood arrested between old and new dam, a new bund, because the earlier bund was just upstream of that dam, was 0.6 to 0.7 meter, and the overtopping of the dam could have caused the flood. And he suggested that the dam should be rectified and breach section should be restored. This is a Google map of that. Now this is the old dam, and this is that spillway of the old dam, and this was existing there, and this is the new spillway for the new dam. And the dam fell from at this portion, and there was 2 outlets, one at this end and one here, and this outlet was also washed out. Now the spillway width is of the earlier dam is small, and this is large, but the depth of this spillway was likely more. But when we went there, it was all filled up with water, without muck, and we could not check the depth of this spillway. But the top of dam probably was nearly the same for both these dams. Now, on the report of that member DSRP, then Dr. Y.K. Murthy again had some observation that the distance between top of spillway and crust and top of dam was 2.14 meter, which can allow discharge more than 180. Because he said the dam has failed due to overtopping, then Dr. Murthy's observation was that the distance between the spillway crust and the top of the dam is 2.14, and 2.14 can discharge around more than 300 cubic of discharge. Therefore, this could not be a reason. And the photographs, what he showed was also not matching with this statement. And there were no signs of overtopping as per the photographs. So he said the failure could be due to shear lineament. Actually, as per the geological report of that area, there was a shear lineament in that area, and he was suspecting that some shear failure might have occurred, and below the foundation there is a shear lineament, and it could be due to that shear lineament. And he suggested that it should be thoroughly investigated so that the next time it should not fail. Then CWC and JSI team went there to investigate that project, and to ascertain the cause of the failure, then we listed all these 4 items and investigated each and every item. Then one was the overtopping due to the high flood, then the failure of foundation due to shear element, then overtopping due to wave action, and then slip failure of the earth dam. Now, overtopping, when we consider that how to check the overtopping, was the first is the water level mark on the spillway was only 1.5 meter, but there were no signs of the flood mark in the upstream of that spillway. The crust level, only a small portion of the crust level was concreted, and rest the thing was soil and which are covered with vegetation, and already 6 months had passed and we could not see any there. But as per our experience, the water level in the reservoir should have been more than whatever the water level at the crust, because of the this approach velocity and this water profile. And when we calculated with our codal provisions and all this, the water level was more 20 centimeter more than, and with that 1.7 meter, 120 centimeter more than the water level mark, we calculated that the discharge was 218 meter, 218 cubic for the, which was matching with the flood hydrograph. And if this is the condition, then it cannot overtop, because 1.7 meter is very much below the 2.14 meter gap between the top of the dam and the spillway. Then the shear lineament theory. The existing section breached, that when we saw the actual breaching portion, it was 2 to 3 meter above the foundation, and the shear lineament was suspected to be below the foundation. And that chances of failure from the shear lineament angle was not suspected. And even the geologist who was there with us, he interpreted from the regional geology and extended the shear plane, and it was crossing somewhere near the spillway. And therefore, it was not anticipated that the shear failure is there. Shear lineament failure is there. Then the overtopping. Now, we asked them to supply the cross sections, a different cross section of the dam, and they found that the dam had settled by more than 30 centimeters in different places. And the 45 centimeter was near to the place where the slip had occurred. Then we ignored that 45 centimeter value, and with 30 centimeter value, and with the, we calculated the freeboard. Now, I'll just show. Now, actually, the main river comes from here. And because of this, no wave could have crossed this and hit this here. And the failure was there. We calculated a wave height considering this length, and we found that the wave height was, we required a freeboard of 0.64 meter, and a significant wave height was 0.41. And considering all these factors, the freeboard was only 14 centimeter available, with the 1.7 meter above the crust water level and 30 centimeter settlement in the dam, and there was only hardly a freeboard of 14 centimeter. And even a significant wave height could have crossed it. That was one reason we could ascertain from this analysis. And then the failure of the dam due to this slow failure. Now, actually, this slow failure, the dam had full rainfall for 9 hours, and the whole dam was saturated from upstream to downstream. And with the photographs available, there were some chances of anticipating that the dam had failed due to due to slip failure. And the slopes which are provided there, because we are not having any properties of the material, we could judge that the slopes provided are not sufficient. And on all these basis of conclusion, we anticipate that the failure was either a slip failure or triggered by a wave action, and the dam failed. Now, the basic, what were the codal provisions, they are not followed, and the state of the art which made the dam fail. Spillway should have been designed for SPF, freeboard should have been provided as per codal provision. No water cushion was provided. Now, all the drop walls, we'll see the photographs, there were at the drop, the floor was horizontal, there were no water cushion on the downstream side, and due to that, all the spillway was washed out. Then stability has to be checked for all the conditions, including seismic. Then siltage, there is actually mining upstream of the dam catchment area, and all the mining waste comes into the reservoir, and due to that mining waste, both the outlets were not working. The silt had already come half meter above the sill level of the outlets, and they were not able to operate the outlets. And the people in the downstream were using this dam as a recharging ground, and they were pumping water from the downstream only before the failure. And the lack of maintenance also, there were no maintenance of the seals because the outlets were not working, they had not done any maintenance to these issues. Now, this is the breach portion of the dam. See the siltation, sedimentation which has been, mining waste which has been deposited upstream of this. This is the photograph on the upstream side. This is that photograph of the failure of that outlet part. This is that spillway portion, the heavy damage. Now, this was the only that slip failure at this. Now, this is the downstream side. From there, we can anticipate that this is a slip failure. This one. This is the downstream side, and we could not anticipate that a wave has crossed it, or probably it looks like a slip failure only. And the corner no overtopping was seen in that site, and it was not anticipated that the water had trapped into that corner and it has overflowed from that place. This is the downstream that existing dam and siltation in the upstream, the reservoir area. Thank you.
When there are so many veterans are sitting here, I am a director from Geological Survey of India, Government of India with some standing. It is always easy to blame in a dam failure geological condition and always a geological surprises, which clearly says a lineament is different, a shear is different. What it has been shown is a covered area. There are number of other aspects are there for the failure. It is every time it is a common problem, and geology comes to the rescue of any failure. I think with so much of experience from the Government of India organization, if I don't react to this, I don't find any other time to say this.
No,
There absolutely it is a covered terrain, a lineament, no geologist can easily go and track also. There are thousand and other one reasons to say the site itself is wrong, whether it has a partial cutoff or a full cutoff, or what are the material. There is no other condition going straight away to the geology, to the convenience of the failure. It is strongly objected, and it will happen number of times, and it is to be resolved. If this forum is at the maybe concluding session, I may be given a 5-minute talk for the dam safety and the geological perspective, which is not covered in this whole seminar itself. I am very sorry to say that. There should have been a chance should have been given to geological aspects and the dam safety, which is ignored totally in this seminar.
I'll just say, there was a representative from GSI also, and he.
Thank you, Mr. Henda. Thank you, Mr. Henda, for
Thank
your favor. I think we can have a discussion afterwards. We have one more presentation by Dr. Sanjay Rana, Product and Services Business Person Overseas Private. Please conclude in 5 minutes. 5 minutes, please.
Sure, sir. In fact, I have done most of my presentation yesterday. So this is a privilege I got in the commercial section. Anyway, I'll make it fast. It's actually a pleasure to be speaking in the concluding paper in the concluding session. In this World Cup season, I'm the finisher, I think, of this seminar. So it's a pleasure to be here. And very briefly, I represent Parson. And Parson is basically a geophysical company. And we are known for the innovations we have been doing in the field of geophysics since inception, including introduction of GPR technology in 1996 in the private sector. I do not claim anything about the government sector. Shear wave seismic refraction in 97, high resolution seismic tomography in 98, and passive seismic tomography in 2008. And innovative use of geophysical methods for high resolution non-destructive testing of dams, which we started as early as 1998. And since then, we have been working on various dams on this. Our main strength is our experienced and trained staff. We have offices in Delhi, Kolkata, Bahrain, Egypt, and Sudan. And we have work experience in India, Singapore, Oman, Afghanistan, Greece, Saudi Arabia, Bahrain, Kuwait, Iran, Algeria, and Georgia. We happen to be the largest engineering geophysics company in India. We have international associations with SkyTem for airborne geophysics, Seismotech for passive seismic tomography, SolGeo for dam tomography, AmbroGeo for seismographs, and Radar System Inc. for GPR technology. We are the only Indian company having complete integrated geophysical capabilities, which includes gravity, magnetic, electromagnetic, electrical imaging, seismic refraction, seismic tomography, GPR, MASW, REMI, crosshole, and tomography. Our areas of operation extend from oil and gas to mining geophysics, to engineering geophysics, to water resource geophysics, to environmental geophysics, to archaeology geophysics, and geophysics for dam safety. Now this dam investigation part, yesterday I have covered all the methods practically. So I'll just briefly make certain points on why. So this is the most suitable method for regular health check of dams, because this entire conference was on dam safety. And health check is a very important part, especially for the dams which are getting older. And we do not really want to drill into the dams to check the health. So totally non-destructive. Early detection of problems. When we say inspection of dam, that means the visual inspection of dam. There are certain problems which exhibit themselves after some time. So early detection of problems, totally non-destructive, so extremely suitable for a structure like dams. Helps design the rehabilitation programs better and accurately. Helps assess success of rehabilitation measures undertaking. This is again was being discussed in one session today. Once the rehabilitation has been done, it is very important to see what has been the efficacy of the rehabilitation. So this can be checked using these methods. Identification of damaged area inside the body, not visible fractures and voids, zones of seepage, etc. So it gives you more information at low cost and quick. When I say quick, yesterday as we discussed, a typical dam can be investigated in anything between 3 days to 7 days of time and report generated in another 7 days of time. So we are talking of 15 to 20 days of time to do a thorough health check of our existing dam. So that's the strength of this technology we are talking about. Various problems of concrete dam like cracks, degradation, water leaks, landslide in earth embanked sinkholes, masonry water leaks and strength, and various methods are available for that. Since Mr. Chairman has given me 5 minutes now, so I'll not go through this. We have seen it anyway, most of these slides. I'm sorry, all the time I'm taking is in switching the slides, so now it's working fine. These are various images which you get using these methods of the subsurface. This is something new which I wanted to show you. This is seismic tomography, which is done between the downstream phase, upstream phase and downstream phase, and it gives you very good information of the internal condition of the dam material. So this is again an example from India. 2 such projects have been done, Tungbhadra and Chimoni in India. And this is from one such project where these low velocity areas basically are the areas which are of concern, which show low seismic velocities. So you have the P-wave velocities here, which again can be converted into density tomography from P-wave velocity tomography, and gives very detailed information on the material properties inside the dam. These are the areas of low seismic velocities. These are all the setups for doing these. This same thing also can be done between the gallery and the top of the dam. And again, the anomalous zones can be very easily detected using this method. So very, very strong technique to do a complete health check of the dam. In India, we have already done a number of dams, including Daroli in MP, Tigra Dam in MP, Mulla Periyar in Tamil Nadu, Madikeda in MP, Amrawat, Temghar in Maharashtra, Tungbhadra in done by Solgio, who is our partner in India, Chimoni in done by Solgio, and at present we are doing Kanhir Puja, Kutiyadi, and Malankara in Kerala. So to conclude, geophysical techniques are a very important tool for health check of dams. Regular monitoring. Regular monitoring is the key point here. Like I don't know, like through this this conference, I'd like to make an appeal. If we can make even a duration of, let's say, 5 years or 10 years for important dams, where this kind of health check can be conducted, I think we can save on a lot of cost, which otherwise comes when we have to do the rehabilitation. Pre and post rehabilitation inspection. This is another important point which I would like to put across. An indispensable tool needs to make part of regular inspection process. Whatever inspection process I'm aware of basically is more of physical inspection, visual inspection. If this can be made part of it, I think it would be good for the industry because it saves costs, time, and reduces risk. With this, thank you very much, and I look forward to see you in the next conference. Thank you.
I think,
Sorry, sir?
I think you can talk to him
Sure.
during tea time. That's
Sure,
fine.
sure, sure.
So now I would like to call one more presentation, Hydrology Review Study of Vaigai Dam by Mr. Batmanaban PW. I would like you to be brief and only present your conclusions.
Respected dignitaries on the dais, my dear friends and colleagues, first I thank you for giving me this opportunity to present my paper, though it was not in the list. Actually, the hydrology review of Vaigai Dam, which is a large dam, has been done by Central Water Commission, and the PMF has been worked out around 9,000 cumecs. But we were very much interested in redoing the hydrology because the existing the spillway capacity is only around 1,783 cumecs, and in our opinion, it is not possible to expect such a very high flood. So we had gone through the review and we made an attempt to re-review the hydrology. We took 2 points for re-review. First of all, the catchment response function was arrived by CWC using the flood estimation report of Zone 4C. In that, we adopt an equivalent slope, which is an average for the catchment. But seeing the catchment, we have, this is the catchment of Vaigai Dam, and it consists of 3 subcatchments, namely main Vaigai stream, this is the main Vaigai subcatchment, this is Suruliyar subcatchment, and this is the Teniyar subcatchment. So by working out the actual slope of the streams, all the 3 streams, we found that the stream is very steep in its initial reaches. Afterwards, from the contour 400 onwards, it is running on a very flat terrain. So adopting a uniform slope may not be actually reflecting the catchment. Adopting an average slope may not be representing the catchment. So we tried this time area method. In this time area method, isochrones are drawn to find out the area of equal travel time, and we worked out the time of concentration also by subdividing the streams itself according to the slope, and we arrived the time of concentration by segmenting it. Yes. Yes. So by doing so, we have arrived the also the rainfall which was taken for the study, for the review, is from Devikulam, which is located on the Kerala, and it is on the windward side of the Western Ghats. And our catchment is on the leeward side, so that rainfall is also not, we found it not suitable, and we took the rainfall which was very severe in the same catchment itself. So by doing all these calculations, we found the PMF to be around 4,500 cumecs as against 9,000 cumecs. We request the Central Water Commission to consider our request for re-review of the Vaigai Dam PMF. Thank you. Thank you.
Now question session starts. Whoever is interested can make one question. In the first paper, a brief study of force dams gave. Yeah. Okay, then you have said on which topic?
Good. I'm from NHPC. The criteria of upstream deflection of the arch dams is very interesting to me. And may I request the chairman, sir, to allow the presenter to complete his paper.
No, I didn't quite
I mean,
understand. Could you repeat
and,
last
and,
sentence?
and it's the cracking, the subsequent cracking in the upstream, in the upper galleries. So that finds interesting to me. I mean, so.
Could you repeat? You are talking about upper gallery.
Yeah, upper
What?
galleries, yeah. The subsequent.
Why it's currently happening there?
Yeah.
Of course.
Is it based on 3D modeling, or is it your experience over certain 3D?
Now it is clear to me.
Yeah.
Now it is clear to me.
I would
You see, my colleague, there is a number of recent publications, especially those of ICOLD, which are very respectful ones, which emphasize that problem in a number of arch dams throughout the world. That one of the unusual phenomenon of arch dam behavior, apart from that which is upstream deflection, is the cracking of upper gallery, and that cracking is almost continuous along the width of the dam. That was written there. I explained why, if you wish me to repeat that, why, according to the authors of that article, it is currently happening. It is, to our mind, it is because of interaction between swelling process, if any, in the dam, and the current service stress conditions in the dam. When you have the compressive stress conditions, they counteract swelling process, diminish swelling process.
Excuse me, Mr. Kovic, if you don't mind, why don't you interact him directly during after the session?
Okay. Why it is so? No, the article the topic of the article was arch dams, not the other dams, please. Other dams might behave differently.
Okay, thank you, sir.
With pleasure.
We are already very late for concluding this session, 40 minutes late. So we had a 5 plus 1 6 presentation, and the last one was by the presentation by a sponsor, that is person, and course is limited. The presentation was good. I congratulate the presenters for presenting their papers nicely in this form. I would like to now request co-chairman to say a few words on this.
Well, I have a number of valid issues to be taken up, but because our time is short, I'll not take them up now. Anyway, I'll thank all the authors for their very good effort and the presentation. But the way I said, whatever I have on my hand, they are very relevant and they have not been addressed in this forum. And they all relate to dams and what we are facing today in our real life situation, when the designs and the design has gone from government side to the private developers. And there are certain things which are to be noted, but the time is short, so I'll stop here with a word of thanks to the organizers and to everyone here.
I thank the organizers for giving us an opportunity to be here and to chair this session. Thank you.
Now after the ending of the session, now I request the chairman to hand over the momentum to the presenter. So first I request Mr. Jaikas Simozokis to be on dais. Please, sir. Next, Mr. C.S. Mathur. I request Dr. Raghukant. N. Srinivasan, Mr. N. Srinivasan. Srinivas. Mr. Y.K. Handa. Now I request the co-chairman to hand over the momentum to the chairman and the rapporteur. Then as a return gift to the co-chairman from the chairman. Thank you.